Hey everyone, welcome back to my channel. So right now we have an hourly time series of electricity production. The resources are renewable energy. And from this time series, I want to try to do long-term forecasting, which is forecasting for a longer period. More specifically, I want to try to forecast the production for the last quarter of 2023. So from October to December. Assuming that we have 30 days in a month and we have 24 hours a day, so the total values we want to predict would be more than 2000. Now there are two types of multi-values forecasting like this. The first one is the recursive strategy, which is we forecast one value at a time. We forecast one value and then use that value as our data to forecast another value. And the second type is a direct strategy. So with the direct strategy, we just predict all the values that we want to predict at once. And that's what we're going to do. More specifically, the model that we will use and learn today is NHITS. This is a deep learning model which is designed specifically for long-term forecasting. Okay, let's study together. So NHIT stands for Neural Hierarchical Interpolation for time series forecasting. So I guess the time series word here is obvious because it's for time series forecasting. And then for the neural is also obvious actually because it's a neural network. But to elaborate on this one, it's an MLP based network. MLP is multi-layer perceptron, aka fully connected network. So here's a simple fully connected network. We have one layer of input, one layer of hidden layer, and then one output. In NHITS though, we would have two outputs in several networks. And then, yeah, it would be several blocks of such network like this. Okay, we will see that in a moment. And we will use a lot more neurons than the one that is illustrated here, and perhaps more hidden layer. In this particular image, we have only one hidden layer, but in NHITS, we might use two or more. And now for the hierarchical interpolation here, it's called a hierarchical because the model will see the time series using different frequencies. In other words, it will use multi-rate input sampling. Okay, and then it is interpolation because NHITS use interpolation functions to generate the forecast and backcast sequences. Hierarchical interpolation is one of the main characteristics of NHITS. Additionally, it also has the multi-rate sampling and doubly residual stacking. Okay, now let's deep dive into the first characteristic of NHITS. Multi-rate sampling means that, as I said earlier, the model process the time series using different frequencies. Now let's see how the model really implements this principle. First, we need to look at the model first, okay? So this is the model, the full network. The model is comprised of several stacks. So the input, the raw time series would go to stack 1, and then stack 2, and then stack 3, and so on until stack S. And then the output of stack S would generate the global forecast. Each stack consists of several blocks. Now, I haven't drawn the connecting lines between the block. That would be, yeah, I'll show you that later, okay? Anyway, so each stack has several blocks, and each block consists of several layers like this, and this is the foundation of NHITS. The very first layer is max pooling, and this layer is where the multi-rate sampling happens. Max pooling layer would help the block to focus on a certain frequency. So what it does is that max pooling layer would generate a kernel with size k. The size of kernel will be different depending on the location of the block. So the closer the block to the input, the bigger the size would be. Let's go back to this picture. So because each stack consists of blocks, so we can draw the blocks like this. We can imagine that the whole model will have lots of blocks that are ordered like this. Since I'm drawing it like this, so the input is on the top and the output is at the bottom. So well, we can say that the higher the block is, that the block in this area would generate bigger kernels than the blocks at the bottom of the network. Okay, and then the kernel would be put on the input so that it will meet a subsequence of the input and then take the maximum value of that subsequence. After that, the kernel will shift by one value and then it will meet a new subsequence and will take the maximum value of that subsequence and so on. Okay, so the output of max pooling layer would go to a MLP stack. So this is a fully connected network with more than one hidden layer. Okay, and the output of that would go to two different places, which is, well, both of them are MLP, but each MLP layer learns different things. So on the left, they learn, this MLP layer learned the interpolation coefficient for the forecast. And then in the right one, they learn the interpolation coefficient for the backcast sequence. So the output of these is the interpolation coefficient, which is denoted by theta. Theta f of L means that it's the interpolation coefficient for the forecast sequence of block L. And the B here on the right is to denote backcast. The output, the interpolation coefficients are used for interpolation function, for interpolating. So this is where the hierarchical interpolation comes in. And the output of that interpolation layer would be the forecast and the backcast. We denote the forecast by a hat, so it's y hat. And we denote the backcast by a tilde. The backcast outputted by the block is like making an approximation to the time series. So if we make a time plot of all backcast sequences from all blocks, that would be the complete decomposition of a time series, of the input time series. And then for the forecast from all blocks would be aggregated into the global forecast. Okay, to know what exactly happens to the backcast sequences that is outputted by each block, we need to look the model from the stack level. Okay, so this block, each block generates a forecast, right? And so that would be aggregated here to generate the stack forecast. So we saw the global forecast earlier when we saw the model from the highest level, but now we see stack forecast. So this is the forecast from the stack level. Okay, now for the backcast sequences, this is where W residual stacking comes in. Okay, so residual here is like in ResNet, residual net. That's the same principle used here. So in short, the backcast of a block would be subtracted from the input of that block. Okay, let me repeat that. The backcast of a block, let's say the block 1 output a backcast, that would be subtracted from the input of block 1, which is the stack input. Well, if we're talking about block 1, that would be the stack input, or the stack input. What I was trying to say was, if we're in stack 1, which is the closest stack to the raw input, then in this case, the backcast of block 1 would be subtracted from the raw input. Okay, so they will meet here, and then we take the difference of the input of block 1 and the backcast from block 1. And then the result of that would be used as the input of block 2. I'm going to denote that with a different color. let's say it's yellow here. So the yellow vector, if you will, the yellow vector would be used as the input of block 2. And then the backcast of block 2 would be used to subtract from the input, which is the yellow earlier. It keeps happening like that until the last block, which is block B. Block B will also generate the forecast, and the backcast would be the stack residual. Okay, and this stack residual would be the input for the next stack, which is the first block of the next stack. So you see, the process is repeated over and over. This is the recurrent aspect of the LSTM. Okay, so that was the second trait of NHITS, which is doubly residual stacking. Now, before we move on to the third one, I want to talk briefly about this notion about expressiveness ratio of RL. And this is actually why we need interpolation. So if we have an input, let's say of length 1000, the simplest way to process this using a neural network would be using a layer with 1000 neurons. But that means the total parameters that need to be learned would escalate very quickly as we have longer and longer input time series. Therefore, that would be computationally expensive and more prone to overfitting, because too many parameters can lead to overfitting, right? And so to avoid that, we want to make a network with less parameters. And how much less? That is determined by the expressiveness ratio. So the length of the interpolation coefficient vector would be R, L. L is the block L, by the way. It's not L for the length as I mentioned here, okay? So R, the expressiveness ratio for block L times the horizon. The horizon is the total values that we want to predict. In our case, that would be around 2000. Okay, RL, the index L here indicates that the ratio would be different depending on the block. And again, this will be depending on the location of the block again. So the higher the block, the smaller the ratio would be. As we go further into the model, the ratio would exponentially increase. If we have a small ratio, that means the interpolation would be more aggressive. And yeah, that's what that is already designed. So again, this is the full model. The higher the blocks or the closer the blocks to the input, this is the raw input time series, the kernel size would be bigger and the expressiveness ratio would be smaller. And then as we go down further into the model, the kernel size would get smaller, but the expressiveness ratio would be higher and would get bigger and bigger. Okay, now let's say that we already have the interpolation coefficients. Now we are ready to talk about interpolation mode. Well, this is actually interpolation function, okay. We are ready to talk about this particular layer here. Let me show you again. This one here. So in this layer, they are just using the interpolation coefficients that they already have and the time points to compute the interpolation function and to compute the value at a certain timestamp. So interpolation is basically a function of two inputs. Tau is the collection of the timestamp. The above equation here is for generating the forecasts, while the lower one here is for the backcast sequences. So H here is the horizon, and then L, capital L here is the length of the history. Usually L, the capital L would be ranging from twice the horizon to 7 times the horizon. There are 3 functions of interpolation functions that we can use. The first one here is the nearest neighbor. And then the second one is the linear interpolation. And the third one is the Hermite-Cubic interpolation. Oops. Hermite-Cubic. So cubic interpolation. So the idea of interpolation is like in math, actually. I'm going to give you an example for the linear interpolation. So let's say that we already have t1 and t2, and then we already know the function, the value when t equals t1 and t equals t2. But we don't know what happens when t equals tau. Let's say that this is the function value when t equals t1, and this is the function value when t equals t2, and then we want to know, because we don't know, so we need to guess the function value when t equals tau. If we assume that the function would go linear, then we can approximate the value of tau using this equation, right? Y equals mx plus c. And analogous to this equation, c would be this one here. This is c. The interpolation coefficient when t equals t1. And then m is the slope, and by analogous, this is m. And then x is tau minus t1, and y is the forecasted value that we want to get. Okay, so linear interpolation would be best used if we assume, and if we see the real data perhaps, and we see a linear trend, a clear linear trend, then the linear interpolation would be the best one to use. But let's say that from t1 to t2 is like this, like we have a cyclical pattern, then the Hermite-Cubic interpolation would be suited the best. Now let's talk about technical details, what happens really in practice. Okay, so by default, we will see later in the coding section, in practice the total stack would be 3. So the full model is like this. We will have 3 stacks, and by default we will have only 1 block in each stack. Oops, sorry. Like this. I'm not going to use the default value for the total blocks, but this is the default value. Okay, and then the activation function is relu. The activation function is used in each neuron in the MLP stack. You can check out my video about using fully connected network if you want to know further about activation function. And the total neurons would be 512. That's the default value, and that's what we're going to use. So this is the total neurons in the hidden layer. Well, going back to interpolation to elaborate more. So why do we need interpolation again? Because T1, tau, and T2 are the timestamps that we actually want to have. So that's part of our horizon. But because we have less interpolation, because we have less coefficient, that means we cannot handle each element, each timestamp in our prediction vector. So we might only have the function value for T1 and T2, but we don't have the prediction when the timestamp is tau. I hope that makes sense. Okay, so that's it for the theoretical section. If you want to know further about it, like in the paper, they include some empirical studies, and they also show why they choose the max pooling layer instead of using average pooling layer, for example. You can check out their papers. And this paper, NBITS, is actually, so NBITS is also a deep learning model, and NHITS is built upon AND bits. Okay, so you will see that AND hits and AND bits are really similar. It's just that in AND hits, they add the multi-rate sampling feature and interpolation. You can read AND bits paper if you want to know more about doubly residual stacking. So here we are now in Kaggle Notebook. I'm using Kaggle Notebook because in Kaggle they provide two types of GPU, and one of them is GPU T4 times 2. So there are two GPUs that I can use at the same time. Yeah, it's a long story actually. Anyway, let's look at the dataset first. So I took the dataset from Kaggle as well. It was uploaded in Kaggle by Stefan Komanita. Yeah, if you have Kaggle account, I think you need to have a Kaggle account to download this. I'm not sure, but you can take a look at it even if you don't have the account. Yeah, this is the columns, so the date time and then the consumption, the electricity consumption, and then the production. This is the total production, but then they also have a breakdown of the production from several sources, including the non-renewable and renewable one. So if you look at it, look at the names, we actually don't have the renewable energy. To get that, I need to do some pre-processing a bit. Okay, so yeah, now let's take a look at our data. First of all, we need to download some libraries. We're using the PyTorch forecasting library to implement NHITS. And since NHITS is written in PyTorch, so we also need Lightning, which is PyTorch Lightning, to train the model. And then here are the libraries that I'm going to use. The basic ones like NumPy, Pandas, and Matplotlib. And then Torch, well, actually, I don't think we will use NN at all, but yeah, it's based on that anyway. And so this is the PyTorch Lightning. And then from PyTorch forecasting, we import a time series dataset. In PyTorch, if we want to train a model, it's like in TensorFlow actually. So we need to start from a dataset and then make a data loader from that dataset and then use that data loader for the training process. And then NHITS, this is the class that, the main class of today's video. And then to measure the performance of the model, the default metric is MASE, but I'm going to use MAE as well because this is the standard metric. Okay, so let's run this cell. The time series ranges from January 2019 to March 2024, but I'm not going to use the 2024 bit. Okay. And furthermore, in the dataset, there are some duplicates, so we have to use the drop duplicate method. Okay, so this is the data, the first few rows of the dataset that we already saw just now. Yeah, as you can see, the column names, there are no renewable energy in the column names. To get the renewable data, there's renewable here, so I make it in this line. To make the renewable energy, we have to subtract the coal and oil and gas production from the total production. And so this is the renewable energy, well, renewable electricity production in Romania. This is the full-time plot, and as you can see, this is the 2024 bit here. As I'm recording right now, it's June 2024. But the latest data is in April, or no, I mean in March, the end of March 2024. And now, well, this is the plot to see the the yellow lines are the total production. So for all resources, including the oil and coal ones. And then the red one is for the renewable one. And this is the production breakdown from each sources. Okay, so as I said earlier, we need a time series dataset in PyTorch to train the data. So yeah, we need to talk about that first. To make the time series dataset in PyTorch, they require ID, group ID, which is to identify the time series, and the time ID. The time ID is actually like the date time, as we can see in here, this one, the first column here. But PyTorch forecasting requires integer for the time ID, so we have to convert that. So that's what I'm doing here. By the way, in this line, we can see that I'm taking out the 2024 data so that our data frame now is full 5 years from 2019 to 2023. Okay, and I make this just for, well, like the placeholder so that I don't need to make an if loop. Anyway, by identifying time ID here, I will take all the data set that is in year 2019, for example, and then calculate the total rows and make that, by using NumPy arrange here, to use that as the time ID. After I have the complete time ID, I would remove the first two values, which I made earlier before the for loop. For the group ID, I just set the year as the group ID. So it's like, oh, this is the time series in 2019, and then 2020, and then 2021, and so on. Oh, by the way, I forgot to toggle the XL so you can see better. Okay. Yeah, the time ID needs to be integer, so that's why I need to change the D types. And for the renewable is our target, right? That's our time series. Because it's a continuous time series. So even though it is an integer right now, we can verify that by checking the D types. Yeah, so the renewable here has the integer type right now, but integers sometimes can be considered as a categorical data. So to make sure that doesn't happen, I need to change the type into float. Now we have the final data frame that is ready to be converted to a time series dataset. And this is our final data frame. To create a time series dataset, that means we need a data of the input, the history, and the prediction. It's like making X and Y's. In the traditional machine learning, let's say, if we're not talking about time series, that means we need to make the tabular data first, the X vectors and the target. We need to make the X and Y's. And yeah, that's what we're doing here. The axis is specified by the maximum encoder length, max encoder length here. So the L, the capital L in our theory section earlier, or like the length of the history vector, would be twice the horizon. Okay, the horizon is set here, our horizon. Yeah, we have 24 hours a day, and assuming that we have 30 days a month, and we want to do it for 3 months. So this is our horizon. And then the maximum prediction length here is our horizon once again. And then here I set which data that needs to be converted into a time series data set, and then which one is a time index, which one is a target. the target and the time varying unknown variables need to be set, and yeah, it's just the way PyTorch forecasting works. Okay, let's run this. And then from the time series dataset, we already made that instance as data torch, right? And from that, we want to split the data set into train and valid. I guess the important one, to understand this block, we need to look at the valid first. We need to start from the valid here. Again, our main task is to forecast the energy production for the last quarter of 2023. So that's going to be from October to December of 2023. That's our horizon. And then to predict that, we need a time series that's which length is twice of that. Okay, so that means in total, including the axis, including the history and the prediction, we have 3 times the horizon. So that's why I slice the data set starting from the last, I just take the last few rows, which is the 3 times our horizon. You know what? Actually, let's just count it. What is 3 times our horizon? 6480. So for the valid data, I'm taking the last 6480 rows from the whole data. Train and valid here would be dataset, time series dataset class. And then to make it work in the training ecosystem, we need a data loader. Okay, so this data loader will take a batch of a data from train or valid, depending on the process it's in, so that the process would be more efficient. Instead of loading all the train dataset or all the valid dataset into the training system, the data loader would just take a batch of it when it's needed. That's why it would be more efficient. To get the data loader, we use two data loader method. And then I use batch size of 256. This is a data distributed training, by the way. So if we have 256 data in each batch, this batch would be distributed across 2 GPUs so that each GPU would have 128 data. Okay, now let's see the valid data time plot. So this is the series that we want to predict, starting from October to December, the last day of December in 2023. As you can see here, the series looks a little bit cyclical, especially here. Well, of course, there are cyclical in the higher frequency, like here, because the volatility it's very clear. But more generally, there is a bit of, cyclical here. So that's why I'm going to use cubic interpolation. Okay, so finally now we're ready to apply the NHITS. First, we have to initialize the class. NHITS with all caps lock except the I letter. And I make that instance named NHITS with all small letters. When we initialize the class, we set the hyperparameters, like the interpolation mode here. The interpolation mode for this library, if we want to apply the cubic interpolation, we have to use cubic X. Okay, X is for the batch. So if I remember it correctly, the interpolation mode or the interpolation function would be applied for each batch. And then, the prediction length is the horizon. And then the context length is the length of the input time series. So in the theory section earlier, it is the capital L. And we already mentioned before, we want to set the horizon, I mean, the context length or the history to be twice the horizon. Okay. And then n blocks here is the total blocks in each stack. Okay, so notice that we have 3 values in our list. That means we have 3 stacks. Okay, we only have 3 stacks in the whole network. And then in the first stack, we have only 1 block. And then in the second stack, we have also 1 block. And then in the last stack, we have 2 blocks. I haven't tried out too many variety of hyperparameters actually, but I noticed that when I increase the total blocks for the last stack, the error would be lower. So that's why I set it this way. The default value would be 111 though. And then for the learning rate, I set to be 2 times 0.001. Oh, sorry, I mean 0.01. It is minus 2 here. The default value for learning rate is actually just 0.01, but I read it somewhere that unfortunately I cannot remember now. That when you want to train across multiple GPUs, the learning rate should be multiplied by the number of devices we have. Since we have 2 devices, we have 2 GPUs, we need to multiply it by 2. It's optional though. Okay, move on to the next one, to the next hyperparameter, that is locking matrix. Here I list out the metrics which I want to use to measure the performance of the model, which are MAE and MASE. We have a series of prediction, but the error value would be just one value, would be a scalar. So let's say that we want to calculate the MAE, mean absolute error. We would calculate the error for each timestamp in the prediction vector, and then take the absolute value of those errors and average them. The basic principle is the same for MASE. All the errors would be aggregated into one value that represent the whole error or the whole metric. Okay, after initialize the class, again, I initialize it with nhits with all small letters. We create the network from there. Okay, we create the neural network from there. To do that, we use from dataset method. The result of that would be used to train the model, to train the network. And then in this method, we put 2 arguments. The first one is train. Train is the time series dataset instance. And then the optimizer. I set the optimizer to be Atom. Okay, so let's run this. So net is our network. Okay, nhits is our class of nhits, the instance of the nhits class, but net is our network. To train the model, we need a trainer. That is, we need to initialize the trainer class. And I'm going to use PyTorch Lightning to do that because it's so much easier to use PyTorch Lightning. It's the higher level of PyTorch. So it's like the wrapper for PyTorch. So to initialize the trainer, we set some parameters like the accelerator. And then since we have 2 GPUs, we just set the devices to be 2, and the strategy is DTP notebook because we are running this in a Kaggle notebook. If you're running this using your own local machine, then you can just do with DTP or DTP spawn or some other strategies like FSDP. FSDP is fully sharded data parallel. Oh yeah, DTP is, by the way, distributed data parallel. So, in distributed learning, there are several types of distributed learning, depending on what you want to distribute. The easiest one, relatively, the easiest one, I guess, is distributed data. So the data is distributed across GPUs, and each GPU deals with a different batch of data. That's the idea of DTP. Okay, and then max epochs I set the epochs to be 200, so the model will go through the data 200 runs, 200 times. Log every n steps means that I want to log the metrics every 10 steps. After we initialize that, we initialize it and name it as trainer. So after that, we just use the fit method. This is the fitting, the real one, the fitting one. And to do fitting, we put the model, which is the net earlier. And net already use n hits. Okay, so that's why we don't see n hits anymore in this line. Okay, and then so we put the model, which is net, and then put in the data loaders. Okay, here we can see that. Oh, actually, yeah, I want to show you the session metrics as well. Yeah, as you can see, both GPUs are used, and the CPU is also all cores are used. Anyway, so this table here is the summary of the network. And we can see we have 10.8 million parameters. So yeah, this is a huge model. So as you can see, the training is in progress. This is the validation loss so far and the train loss so far. Each epoch runs quite fast since we have 128 data in each batch. Yeah, now as we can see, the training is over. It starts with epoch 1, so it ends with epoch 199 because we have 200 epochs. Now, there are so many warning messages here, but don't worry. Alright, so after we train the model, the next step is to predict it. And so the net here is in the state fitted. So the net is already fitted, therefore we can use the predict method of net to predict the energy forecast. Using the data is using the valid data loader. And then usually for prediction, we are not predicting across GPUs. So yeah, I just set the accelerator to the CPU. Now that it is done, let's calculate the error using MAE. We put in the prediction and the real value. When we predict earlier and save it to the energy forecast, we set the return y to be true and return x to be true as well. So return y, that means returning the real value as well. Okay, so we can access the real value and the prediction just from one object. The MAE is a little bit more than 600. This is quite in the low area, the low values that I got with several trainings. I tried several times and mostly with linear interpolation. I guess the lowest one with linear interpolation is 637, if I remember it correctly. I don't know if I can show it to you though. Yeah, maybe I can show it to you with another with another notebook. But yeah, I'm not showing it in this notebook. So to interpret this number, it means that on average, the error of the electricity production would be 606.3 megawatts per hour. Yeah, maybe this sounds a lot, and yeah, maybe we can try more. We can try more parameters, changing more parameters. So far, I only try to change the total blocks and the interpolation mode. I also try to increase the stack. So instead of only 3 stacks, I try to add 4 stacks. I really hope I can update this project someday. Anyways, let's move on. The rest of the cells are just visualizations of the model. So in this cell, I plot the real value and the forecasted value. Maybe I should do it. Wait, sorry. Right now, the blue line or the forecasted value are covered by the real value. So we cannot really see the forecast really well. I'm going to switch this up. So the orange color one is the real value, while the blue one is the forecast. And yeah, as you can see, the forecasted values are not as fluctuated as the real one, but the direction is there. We can see that when the real value is decreasing, the forecasted value is also decreasing, like in this part and this part, except for the beginning of the series. At the beginning of the series, the forecasted tends to be over forecasted. Okay, and then for the next one is plot interpolation method. So the network after fitted, they have this method of plotting the interpretation. So they can plot the results from each stack of the model. Okay, so the blue line, especially, oh, here, I should show it here. Yeah, the x-axis is shared through the subplots, and then the time, if it's minus, that means it's the history. Okay, the positive time means that it is the predicted value or predicted series. And then we see three here because we have three stacks, the green, the purple, and the red. If we see, well, actually, because we have double plots here, they are the same though. So this is the first one and this is the second one. They are exactly the same. I don't know why they have two plots like that, but we can use it anyway. So the purple one is from pooling size of 1. The pooling size is from the max pooling kernel size, I guess. The pooling size is the smallest one, so it is the pooling size of the max pooling in the last stack. Recall that as we go further and further from the input, the kernel size would get smaller. Or in other words, the closer the stack to the input, the bigger the kernel size would be. Okay, so the biggest kernel size is 1024, and that is produced by the green line. So the stack, yeah, the green line is from the first stack, and then the red one is from the second one, and the purple is from the third one. It looks perfectly horizontal for the red and the green line. I don't know if it's because of the y-axis scaling, but yeah, if it's really horizontal, then I'm starting to guess that perhaps if we reduce the total stack, perhaps we can get a better model. Okay, so that's it for today. In this video, we learned about NHITS, how the model works, and how to apply it to create a long-term forecasting, a decent one, using PyTorch forecasting. Thank you so much for watching. If you enjoy watching this, please consider subscribing to my channel, Timely Time Series. Don't forget to share and comment and like the video. And I'll see you next time. Bye-bye.